Thank you for inviting me to this workshop. It's a great pleasure to be here today. I will be presenting a joint work with Gilbert from MPI, Benjamin Grégoire from INRIA, David Pichardy, and our current and former PhD students, Rémi Hutin, Vincent Laporte, and Alex Trieux. In my talk, I will tell you about an approach to make a compiler secure with formal guarantees. The starting point is an existing compiler that comes with a machine-checked proof that no bug is introduced during compilation. The goal is to turn such a correct compiler into a correct and secure compiler. In other words, we first define a security policy related to source programs, and then we guarantee that it is preserved through compilation. The notion of security we address is cryptographic constant time. It is a popular software-based countermeasure to protect cryptographic implementations against timing and side-channel attacks that exploit the execution time of programs. Informally, an implementation is cryptographic constant time if its control flow and sequence of memory accesses do not depend on secrets. This notion differs slightly from the notion of constant time used for estimating worst-case execution time of programs. This is why we call it cryptographic constant time. However, in my talk, I will use only constant time to mean cryptographic constant time. So, let's suppose I am implementing a new block cipher in C, where I know the secret keys I want to protect against a side channel. I will follow the constant time programming discipline and write a program that cannot use the code snippet I've shown on my slide. Indeed, in this small function, there is an if statement with a condition that is a secret value. So this function is not constant time. Instead of using this function, I will use other function. I could use any of these two functions, and I will choose the second one as it is more efficient because it uses bitwise operators. So this is a toy example, but in the literature, there are cryptographic constant time implementations of many cryptographic algorithms. Building correct, efficient, and constant time libraries is very challenging, and expert developers occasionally fail to follow this policy. So several verification tools have been built and used for checking that popular library follows a constant time policy. But this tool targets low-level implementations for efficiency reasons and because the policy is related to the running program, that is the compiled program. But checking low-level implementations is tricky because the analysis work is harder. For instance, performing an alias analysis at low level is more difficult than performing it at source level. Moreover, when a tool finds some errors, it is more difficult to explain them to the programmer. In a previous work with David Pichardy and Alex Trieux, we provided a verification tool operating at source level and based on the Veresco abstract interpreter. Starting from secret values given by the user, our analyzer infers statically all the secret values of the program, and thus it may ensure that a source program is constant time. Okay, so when we have such a tool operating at source level, we then need to ensure that the constant time policy is preserved through compilation. So what we need is a secure compiler. A secure compiler is a compiler that comes with the following property. It is a theorem that states that for any source program P, if P is constant time, then so is the compiled program. Preserving constant time through compilation is not straightforward And former versions of Slang and GCC compilers did not preserve it on simple programs. Here is an example. On the left, you can see the 3 code snippets I've shown you before. And so among these 3 programs, 2 are constant time. On the right, you can see the compiled version of this program. And what we can see here is that all the compiled programs are not constant time. Indeed, we can see that the compiler added a GNE instruction that is a conditional jump depending on the result of a previous comparison, which could involve a secret value. Another example of a compiler breaking the constant time policy of a source program is the conversion from an integer to a floating point type, which is constant time on the source program on the left. However, once again, the assembly code shows that the compiler introduced a conditional jump instruction. So once again, here the compiled program may not be constant time anymore. I showed you toy examples of well-known programs, but in the literature there are other examples of real programs that were supposed to be secure, but were found not to be constant time. The first example concerns different implementation of the TLS protocol. And here on the right, this second example is another implementation of this protocol. Interestingly, this implementation was vulnerable to timing attack, even if it undergone 3 different security audits. So to sum up this first part, I introduced the constant time security policy, and I suppose that I have a tool able to check it on C programs. Now I need a secure compiler that preserves this policy. So in the second part of my talk, I will introduce a CompCert compiler that we reused. Then I will explain how we turned it into a secure compiler. If you want to prove something about a realistic compiler, then you probably want a machine check proof. This is a field of formally verified compilation where there is a milestone named CompCert. CompCert is a moderately optimizing compiler for C that is specified, programmed, and verified using the code proof assistant. So it is now used in commercial settings and for software certification by safety authorities. CompCert comes with main theorems. This theorem states that the compiler does not introduce bugs. It is a semantic preservation theorem stating that observational behaviors of program are preserved. It relies on numerous theorems, including theorems related to the preservation of the memory safety, where in CompCert, the memory model is shared by all the languages of the compiler. However, in the CompCert development, there is no theorem about side channel attacks. So starting from CompCert, we first define precisely what secure compilation means for constant time. Then we prove that a mildly modified version of CompCert preserves the constant time policy. I will explain how we turned CompCert into a formally verified secure compiler. The challenge was here to reuse existing proofs as much as possible without breaking these existing proofs. Our last contribution is a proof methodology for doing such a thing, and we hope to reuse it for other security policies. So first, I will give some background on CompCert. CompCert accomplishes a series of passes from C down to assembly using many intermediate languages. In this work, we start from the C-like source language. It is a deterministic language, and programs are compiled down to x86 assembly using 17 compiler passes. The peculiarity of CompCert is that each of these passes is proved correct. There is also a general theorem stating that the sequential composition of 2 passes is correct as soon as both passes are correct. So we have 17 passes to prove secure. And so we have 17 proofs to adapt to preserve our security policy. To avoid conducting these 17 proofs separately and to do them from scratch, we need to define a proof methodology. So let's look more closely at existing proofs. So each correctness theorem is a semantic preservation theorem. This means that for each language of the compiler, there is a semantics defining this language. So each language is given an operational semantics that models a small step transition from a state to another state by emitting a trace of external events. The printing of a value is an example of such a trace. And then, once we have a small step relation, we can define the full execution of a program. It is a reflexive transitive closure of the small step relation. And so the full execution of a program observes a trace of events. And this execution can be infinite. So for our 17 passes, proving the correctness of a pass from a source to a target language amounts to proving a forward simulation diagram, stating that each statement of the source program is executed in a similar way in the target program. More precisely, we first need to define a matching relation between semantic states of source and target languages. Next, for every step from a source state S to a source state S prime in the semantics of the source language, and every target state sigma that matches with S, we must prove that there exists a target state sigma prime such that sigma prime matches with S prime, and sigma prime is reached in at least one step from sigma. Moreover, the emitted trace must be the same in both executions. Furthermore, some statements are not compiled and do not exist in the target program. For such statements, we need another simulation diagram that states that a source execution corresponds to no execution in the target program. In such situations, the trace must be empty, and we use a measure associated to the source state that decreases to ensure that there is no stuttering steps that can happen because of infinite executions. So, after this background on CompCert, I will explain first how we define our security policy, and second, how we modified CompCert to preserve it. So, let's see how we defined our security policy. We defined two new events observed by the CompCert semantics and modeling potential leakages of secret values. So a leakage is either the truth value of a condition or a pointer representing the address of memory access, that is a load or a store, or a called function. So we have these two new events. They may be observed by the semantics, so we need to adapt all the CompCert semantics to observe these leakages. We then have an extended semantics, and with this extended semantics, we can still reason on the CompCert semantics by erasing our new events. We call this semantics the compile-only semantics, where leakages are erased. And this semantics is used to prove the correctness of compiler passes. Moreover, we can also reason on the leak-only semantics by erasing all the events that are not leakages. This is interesting because our security policy is related to this leak-only semantics. So coming back to our constant time policy, let us note that this is an indistinguishability property as it involves two different executions of the same program, contrary to CompCert correctness property that involves a single execution of a program. So we introduce an indistinguishability relation, phi, between initial states of a program. It expresses that these states share the same value for public inputs, but may differ on secret values. We say that a program P is constant time secure with respect to phi when for two initial states that are related by phi, then both leak-only complete execution of P starting from both states observe the same trace of leakages. So the main theorem is the following. Let P be a safe C-like source program that is compiled into an x86 assembly program P prime. If P is constant time secure with respect to phi, then so is P prime. So this is a security property we expect from our compiler. And now let's see how to prove it in Coq and with the help of the existing CompCert proofs. CompCert is 100,000 lines of Coq, so modifying the CompCert development is really a matter of proof engineering. We spend a lot of time thinking of the methodology to follow before starting our proofs. So on the one hand, our security property is related to the leak-only semantics. And on the other hand, there are simulation diagrams related to compile-only semantics that are already proved in CompCert. So how could we reuse them? So we start from the existing proofs. And here, let's imagine we have a diagram about a compile-only semantic with a proof script. So something that is already proved in CompCert. So we have this diagram that is already proved. So we have a proof script. What we did is as follows. So we slightly modify the diagram in different ways that I will explain later. But during this modification, we make sure that this modification still implies the previous diagram for the compile-only semantics, so that we will be able to reuse the existing lemma for CompCert correctness. So this theorem is a generic theorem. We prove it only once for all and not for any language. Then, as we have modified the semantics by adding leakages, we need to slightly modify the existing proof script of CompCert in order to prove the new diagram. And here, thanks to Coq tactics, we reuse a lot of the proof scripts. So we also have a generic theorem that says this diagram is strong enough to enforce constant time preservation. And once again, we prove it only once for all. So in other words, we conduct our proofs only once in the extended semantics, even if we need two theorems, one for correctness and the other for security preservations. So we have defined 4 ways of modifying a simulation diagram. The trade-off between proof tractability and generality of the method differs among the different techniques. So these techniques range from very simple modification of a simulation diagram to complex reasoning on a cube diagram involving 4 different executions of a program. And interestingly, the first three methods are slight relaxation of the classical forward simulation diagrams. So we were able to reuse existing diagrams for these three methods. So let's look at these methods in more details. The first methods correspond to the ideal situation where the trace of leakages is preserved by a program transformation. So we can reuse directly the traditional CompCert simulation diagram. In other words, we reuse the existing CompCert proofs and only need to fill some holes in the proof. So let's consider two complete executions of a program at a target level. Each execution observes a trace of event. We have two traces, tau and tau prime, and we want to prove that tau equals tau prime. How do we prove that? Well, first, we exhibit the corresponding source state that are also related by phi, and that match with the target state. Because we assume that the source program is safe, we can also exhibit source executions. And because the source program is constant time, they should emit the same trace T of events. Last, because we have proved a forward simulation, then we have the fact that tau equals tau prime. So this example shows that here we were able to reuse almost directly the existing simulation diagrams. Unfortunately, the first method is not adapted to program transformations that modify the trace of leakages. So we have defined a second method that is adapted when leakages are erased by a transformation. This is adapted, for instance, to register allocation. Indeed, register allocation may replace a memory load by a load from a register that is a different instruction which does not emit a leakage event. Such a transformation is still constant time preserving as long as its decision to erase this information does not depend on secret values. So we slightly adapted the simulation diagram in the following way. First, we parameterize the simulation relation with a number that predicts the number of execution steps at the target level. So this means that we need to compute this number and keep it in the simulation relation so that we can reuse it in the proof. So now we need to prove a simulation diagram. So as before, we need to prove that there exists a target state sigma prime that matches with S prime and that is reached in exactly n steps from sigma. So this is why we needed n in the simulation relation. If n is 0, then we still have the decreasing measure. Maybe tau is equal to t, and we are in the previous situation, but maybe tau is different because there was some error in t, and in that case, t was a leak-only event. Because we have here at the source level only a single step of execution. So once again, this second method requires only a few changes to the existing proof scripts. Another way of modifying the trace of leakages is to alter the memory layout. Indeed, the memory layout evolves during compilation of a program. And for instance, some memory blocks are added while others are merged. So to relate memories before and after this modification, the memory model of CompCert comes with the notion of memory injections. An example of a path that uses memory injection is the construction of stack frames, where some local variables are put in the stack frames, while other local variables are pulled out of memory. So this corresponds to the picture here on my slide. And in that case, we need to define memory injections. So in our leakages, we may observe pointers, and so these leaky pointers are not preserved by compilation. So we need a memory injection to model how they are transformed. So in that case, we need a more complex simulation diagram involving the memory injection. This means that we need to define this injection, this relation between memories before and after this transformation, and we need this injection in our matching relation. Then, in the simulation relation, we have to explain how this memory injection is transformed. So here, because pointer may be modified, the traces differ between the source execution and the target execution. And so we still have the constraint that these traces must be related by a memory injection. More precisely, we have to make sure that the trace stored in the target execution is a mapping of the trace T of the source execution using the memory injection. So this is more complex, but it still fits in the simulation diagrams. So I will not talk about the last method, the cube method. But in the end, we have these 4 proof methods that we used to prove our 17 passes. So we were able to reuse the trace preservation method, the simplest one, on 6 compiler passes. Then we were able to reuse the leak erasing method on 5 more compiler passes. And then we reused the trace transformation method on 5 more passes. So there is one remaining pass for which we had to use this tricky method of cube diagram. So this is a very general method, but very complex to prove. This method was proposed by Gilbert, Benjamin Grégoire, and Vincent Laporte in a previous publication. But in this publication, they apply this method to a toy compiler and toy optimizations. And when we tried to use it in CompCert, we realized it was very tricky. And this is the reason why we designed other simpler methods, but that were more tractable in terms of proof engineering in CompCert. A few words about the experiment we conducted. So when you have a COC development, you have a proof, but you also have a software, the compiler. So we were able, thanks to the extraction facility of COC, to extract our compiler into own OCaml code and to run this OCaml code. So we compare modified CompCert compiler with other compilers, so mainly GCC at different levels of optimization, and the original CompCert. And we used a benchmark of common cryptographic programs that were shown to be already constant time. So this experimental evaluation is mainly used to validate that our approach is reasonable. Indeed, there are heavily optimized implementations using handwritten assembly or AVX instructions that are not supported by CompCert, that are much more faster. So let's look at the result. So we obtain shorter execution times than GCC without optimization. This is a promising result, as some users who are wary of too aggressive compiler optimization breaking constant time security could use it. Yet GCC with optimizations remains more efficient. And moreover, our modified CompCert is as efficient as the original CompCert. So in summary, I presented a machine check proof that a mildly modified version of CompCert preserves cryptographic constant time, a security policy to protect a program against cache and timing attacks. To conduct this proof, we designed a carefully crafted methodology that maximizes proof reuse. Before this project on constant time CompCert, I worked on another modified CompCert for security purposes, where we designed a sandboxing transformation. So this is a completely different security policy. Our goal was to ensure that an untrusted module cannot escape its dedicated address space. So this is another line of work where we design security enhancing transformation. And as future work, it would be interesting to define other security enhancing transformation that target the constant time policies. More perspectives. So in the future, it would be interesting to extend CompCert with support for vectorization instructions in order to reduce the performance gap with handwritten assembly cryptographic implementation. Another possibility would be to use our modified CompCert to generate probably constant time implementation. For instance, Andrew Appel, Lennart Beringer, and other people at Princeton verified the correctness and security of OpenSSL HMAC using the VST program logic that operate over the C-like language. So it would be interesting to reuse our CompCert to ensure that their implementation is constant time as well. Last, the constant time policy is an instance of what is called observational non-interference. That is a generic information flow policy for side channel leakage. So we intend to extend our proof methodologies to establish preservation of some observational non-interference for a larger class of property. Indeed, our proof technique rely on a non-canceling property of leakages, and we would like to study policies that do not satisfy this property. So this non-canceling property is about two executions of a program where each execution is a sequence of statements. And in each execution, the trace is that the concatenation of two traces. The property states that if the concatenated traces are equal, then so are the elementary traces, provided that their size is the same. So in our proof, we use this property. Informally, it holds for the constant time policy because two executions that have different traces of leakages at a given program point cannot have the same trace of leakages at a further program point. Unfortunately, the non-canceling property fails for other policies, such as the constant resource policy that we are currently studying. This policy defines a notion of resource consumed during the execution of a program. More precisely, we compute a number of primitive operations, and we say that a program is constant resource when this number does not depend on secrets. So this constant resource policy states that an attacker capable of measuring the resource consumed during a program execution cannot deduce any information on the secret of the program. For example, the following program is constant resource as both branches consume the same amount of resources. That is 6 accesses to variables, plus 2 additions, plus 2 multiplications, plus 2 assignments. This policy is interesting as it tolerates branchings depending on secret values, as long as the branches are balanced in terms of resources, which corresponds to what some people and some verification tools do in practice. However, because leakages are not constrained in balanced branches, the non-cancellation property fails for this constant resource policy. So we would like to formalize this constant resource policy as we did for constant time and show that it is preserved through compilation. Contrary to the constant time policy, this would require to adapt the compiler passes as they may break the balance between branches when they reduce the resource consumption. So we would need to add some security enhancing passes that preserve the balance of a program. Indeed, coming back to the former example, an optimization such as common sub-expression elimination will transform the program into the second program that is not balanced anymore, as for instance, the number of additions differs in both branches. So this program is not constant resource. A way to preserve the balance is to introduce a minimal amount of padding in every unbalanced branch. This could be performed by 2 passes. The first one adds some padding as in the third program, where a new padding instruction called delta is used. It is such that delta of n consumes n resources, so every modification stemming from the optimization is compensated by an adequate delta instruction. The second pass minimizes the padding insertion by factorizing and removing as many delta instructions as long as the constant resource policy is preserved. So this will give the fourth program on my slide. And so this is an ongoing work that we recently started. If you'd like to learn more, here are some references. Thank you for your attention, and I would welcome any questions or comments you may have.
Thank you very much, Sandrine. I know it's hard to do a collective applause on Zoom, but I wanted to do it. I open the stage now for questions. If you would like to ask a question, please raise your hand. Oh, I see Anita has a question. Now you should be able to talk, Anita. Go ahead and ask your question.
Hi, Sandrine. Excellent talk. So one question on slide 29, when you're talking about padding, how does this interact with the optimization? It seems counterintuitive to optimization, but does padding help retain some of the performance benefits from, say, common sub-expression elimination? Hello?
Can you hear me?
Yeah. Yeah, sorry.
Sorry. Yeah.
Okay.
indeed, when we add padding, we add some instructions. And as I said, the goal of this instruction is to get a balance between branches.
Mm-hmm.
So of course, if we could add too many padding instructions, and to avoid this, we minimize the padding. So this means that, for instance, in my example, in the end, we will probably, we should have a padding instruction only in one branch, because it will be a delta of 0 in the other branch, right? So indeed, we need this minimization pass in order to avoid to add too many padding instructions. And yes, in the end, we still have a few padding instructions, and that indeed could change the performances of the program. But our goal is that we should not have too many padding instructions. Another thing that I haven't said in my talk is that we do not intend to do this padding insertion everywhere in the program. So we need to do this only on some parts of the program that should be secure. And so for that reason, we intend in the end to have a very reasonable amount of padding instruction that should not degrade the performances of the program.
Oh yeah, that's a good point. Yeah, I missed that. Yes, so you're only doing padding in the secret zones. So
yes, exactly. Yeah. I didn't explain that, but that's the main idea. So our goal is to use a kind of atomic instruction to delimit the secret zones of the program. So we suppose that we have a previous static analysis that was able to add this specific atomic instruction. And so we will add padding only into these specific secret zones.
Yeah, that's very clever. Thanks.
More questions? Catalin, go ahead.
I'm trying. Does it work?
Yeah.
So constant resource policy, I mean, it's less restrictive than constant time, but I assume that it would only work on very, very simple processors that don't even have caches or any kind of pipelines or speculative execution or any kind of modern features. Is that true? And how, like?
So, as I said at the beginning, our work, we only look at x86 assembly, right? So we do not intend to target many modern processors. So yes, you are right. We will not be able to handle modern things, but our goal was to be closer to what practitioners do or what some verification do, and to allow balanced branches.
Yeah, but I mean, balanced branches will not really hide secrets on modern processors. And I don't think, say, cryptographers would do balanced branches.
I agree with you. Some cryptographer will not do balanced branches on one hand, but on the other hand, if you some cryptographer use tools that allows balanced branches. So this is why we are looking at this policy. I didn't say that this is a unique solution. Just we wanted to study this other policy to see if we can it fits in our model.
Okay, thank you.
We still have plenty of time for questions. So if you have any, just raise your hand. Maybe Sandrine, I can ask a question in the meantime. So, well, Catalina now just mentioned speculative execution. So we're all aware of the latest Spectre attacks, and these are very worrisome. So I was wondering what do you think will be the challenges to adapt the approach, the simulation diagrams that you just described to take into account speculative execution, and how do you imagine these diagrams could help in preserving speculative constant time, meaning constant time under the speculative model?
Okay. So the first part of my answer is that in CompCert, so the goal of CompCert is to generate assembly code. So this means that we do not model at all low levels of the processor and things like that, right? So if we would like to tackle this kind of things, this would require us to model caches, things like that we do not have in CompCert. But on the other hand, yeah, I think yesterday there was a talk at CCS about some people who modeled about Spectre, where they proposed a model to handle different versions of Spectre and so on. And when I listened to that talk, I was thinking that maybe we could do something for to have proofs for related to these models and so on. And if I remember well, they also did some proof, by the way, on their model. So yes, I think maybe we could do something, but yeah. So this proof simulation is, so this is the basic block to conduct the proof when we have a semantics on a language. So maybe we could do something, and so I just realized this yesterday when listening to the talk, so I cannot say you more about this.
Yeah, great. It's, yeah, I mean, I think it's, I would be very curious to see how much we can push these techniques. The one thing that maybe I think could be useful in tackling this problem is that, I mean, what you said is that you need basically a speculative execution model for x86. So for sure that part of the semantics needs to be adapted. However, the other thing that on the other hand, I think maybe you might also need to extend the execution, the semantics at the source to talk about speculation. Yes. Because stating speculative constant time is a semantic property of speculative execution, not sequential execution. So that I think it would be so at least I would say, yeah, for sure the backend, the target languages need to be extended, but similarly also the source languages. And since the CompCert has so many intermediate languages, probably I imagine this will be challenging to find the right way to express speculation in all these intermediate languages.
Yes. So there are many languages, but they are very close one from the other. So, right.
Hopefully, you can reuse the same. They also will be similar under speculative execution. Yeah, that's probably true. Oh, Musard has a question. Go ahead, Musard.
Can you hear me? Hello?
Yes, we can hear you.
Oh, excellent. Yeah, just to add a little bit to the discussion, since I'm one of the co-authors of the paper that Sandrine just mentioned. So it's not very easy because when you get into the microarchitecture level, you have a lot of non-determinism. And what we show there is that even out of order, without non-determinism, then constant time is not enough. So we really need to come up with a new version of constant time if we want to handle these cases, basically. So it's not as nice as it is for deterministic programs that you get at ISA level. yeah, so this was just a comment, but then I had the question. So I guess you have some sort of verifier for checking constant time at source level, right?
Yes.
So how do you do that? What programs can you handle?
So what we did is, so we had previously a static analyzer based on abstract interpretation that operates over C level.
Mm-hmm.
And we adapted this abstract interpreter in order to prove programs constant time. So yeah.
So my question there is very basic. So how do you define the policies? So you mentioned this function phi, right? That
Yes.
determines the relation. I've looked at a lot of work, but that's something that is a little bit sort of hidden in the details. So I guess it's application specific, but is it an obvious way to define these policies, or you just assume everything is high and then?
No, it's not obvious at all.
Okay. I see.
No. So the idea is that we already have semantics of languages. So in this semantics, there is a memory model where we have values and so on. So we can express, for instance, this phi property. But yeah, it's not obvious at all. So yeah.
Okay, I see. So you share the same concern.
Yeah.
All right, thank you.
Any other question from the audience? Maybe I have one question. So if I understand, so follow-up question with respect to the security policy. So if I understand it right, the security policy tells you which part of the memory contains secret data, which memory addresses, right? So probably this is not a problem for constant time programs because normally there is no dynamic allocation of memory and no free memory. But in general, if I think about enforcing just a non-interference property, I would have the same, I would also need to define which memory addresses contain secrets and which do not. I imagine though the runtime system, if my program allocates and frees memory on behalf of the program, now I should actually be very careful about the fact that the address is the security policy of a memory address is now not static anymore, because first I could allocate memory and put some secret data there, then I free it, and now I put public data there, and I have to be careful that I allocate secret data, then I free this memory, so it becomes available again. I allocate other memory, and the memory allocator gives me back that chunk of memory that now is available. So to handle this kind of policies, is that something that is it possible to do in the model that you have? So this kind of dynamic security policy that can change throughout the program? Or
So
to be static?
yeah, no, it's not possible because so I say that the memory model is shared by all the languages. This means that the same memory model holds for C and for assembly. And the memory model is in fact a kind of Java memory model, meaning that you cannot reuse a memory block. So what you did, you cannot do what you did in CompCert. So you cannot reuse a freed memory block that to store a new value. So
what about though like local variables that are allocated on the stack. So
yes, yeah, sure, sure. They are allocated on the stack. Yeah.
And then I could end up though reusing that.
Okay, so at low level you could do something, right? If you change something in the stack, you could, of course, yes, you could do it, but not at C level, not at source level.
I see.
Because
so
we start from a
Mhm.
disjoint memory blocks, and each variable is in a single memory block. So you could do this, but at very low level, where it's difficult to analyze things. Yeah.
So the problem that I'm describing basically doesn't arise in the proofs because it's a problem at the target, but you don't have this problem at the source. So okay, therefore was the.
So the idea is that we want to be able to reason on program, and we want to be able to reason on memory. So if we only have a flat memory model, we will never be able to reason and to ensure some property of memory. So the trick in CompCert was to design this memory model that is exactly the same for all the languages. And of course, the price to pay is that it is a higher level memory model than a flat memory model.
Thank you. We still have 5 minutes before the coffee break. So if you have, I think we have time for one or two more questions. Okay. Oh, wait, one more. Musard. There you go. You can talk, Musard.
Yeah, so since we have time, I'm a little bit curious about this abstract interpretation analysis.
Yes.
So I guess you are sort of flow sensitive when it comes to local variables in a sense, right? So you can copy a secret into a local variable to
yes.
ensure constant time. But when it comes to memory, I guess you can never, yeah.
So we have a precise, once again, we have this memory models. So what I forgot to say is that our Verasco static analyzer relies on CompCert, meaning that we reused existing languages of CompCert. So we reused the memory model as well. And in Verasco, we have a precise analysis of memory, which means that for instance, we are able to taint only a memory cell as secret and not a full array when,
I see.
Yeah.
I see.
Yeah.
Okay, I should look it up. Thanks.